5.3, Day 2, Conditional Probability and Independence. Question 1 asks, how can you tell if two events are independent? In general, for independent events, knowledge about one of the events happening gives no further information about the other event happening. So we say knowledge of one event occurring gives no information about the other event occurring. And then more specifically, the events don't influence each other. For example, your eye color. Let's say your eye color and your height. Those are two independent events. Just because you have brown eyes doesn't mean I can tell how tall you are, and vice versa. Definition of the green box there. A and B are independent events if the occurrence of one event does not change the probability that the other event will happen. In other words, and this is actually the equation, the formula for independent events, the probability of A given B, so given that B's already occurred, the probability that A happens is equal to the probability of A. So it's almost like this simplifies down to just probability of A. It's like, yeah, B happened, but it doesn't really matter. It doesn't really affect it, so it's still just the probability of A. And likewise, the probability of B, given that A has occurred, is just the probability of B. So for independent events, this is really simple. The conditional probability is just equal to like the individual probability. It's almost like the condition never even happened because it doesn't affect it because the two events are independent. Okay, this actually makes for a really nice result when we're combining multiple independent events. So we say like if A and B, for example, are two independent events, we're going to be able to simplify the general multiplication rule, which has to do with the and statement, the intersection. So the general multiplication rule, which we've already learned, the intersection of two events A and B. So what's the probability that A and B happen at the same time? So that's the probability of A times the probability of B given that A has already occurred. But what's nice about independent events, if A and B are independent, you know that the probability of B given that A has occurred, it doesn't even matter. It doesn't even affect B. So that just simplifies to be the probability of B. So we're going to use this to make this general multiplication rule a little bit simpler for our independent events. So if they are independent, the probability of their intersection, probability that A and B occur, is just equal to probability of A times the probability of B. Really straightforward. Just multiply their two individual probabilities. Okay, to summarize that, if two events are independent, we can prove it by showing that their conditional probability just simplifies to the individual probability, like the other one never even occurred. And then when we have multiple independent events that occur at the same time, we want to find the intersection, we can just multiply their two individual probabilities together. So let's look at the first example here. It says, following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977. So for an individual O-ring to function properly, the probability was 0.977. Assuming they succeed or fail independently, what's the probability all six would function properly? Okay, so the first take home from this is that they're independent events. And we actually need all six to function properly. And each one has an individual probability of 0.977. So what's the probability that all six O-rings function properly? Well, since we just learned the multiplication rule, we can simply multiply the probability for each O-ring 6 times in a row. And just to make this a little bit easier, that's just 0.977 to the 6th power. So 6 O-rings, they all function individually or independently. So what's the probability that they all 6 work at the same time? So that's like the intersection here. Just multiply the individual probabilities. That's approximately 0.8697. So that's a little bit risky. To give it some context, that means there's about an 86.97% chance that all O-rings function properly. Which the complement of that would give 13.03% chance that one of them fails. So that's actually a pretty high failure rate here. Okay, question 2. What's the difference between mutually exclusive and independent? And this is a big distinction that kids oftentimes confuse. So let's get this straight the first time. First, let's talk about mutually exclusive events, or disjoint is the other word we call those. So I like to think that has to do with the timing of events. That's the big distinction. Mutually exclusive events, they can't happen at the same time together. Either one can happen or the other can happen, but they can never occur together. So we say two events can never occur together at the same time. Which means if one event happened, you know the other event couldn't have happened. The easiest example I can think of for this is the heads-tails example. If the coin landed heads, you know for sure it didn't land tails, and vice versa. Only one or the other can happen. So that's what mutually exclusive has to do with. Can they occur at the same time? So there is no intersection of events when it comes to flipping a coin. It's either heads or it's tails. So on that same token, if something's mutually exclusive, if two events are mutually exclusive, they're definitely not independent. Because if you've got knowledge about one happening, you know the other didn't happen. So you've got knowledge about the other event too. So they can't be independent. They have to do with the timing of events. Either one or the other occurs. Going back to the Venn diagram, there's no overlap for mutually exclusive events. Either you're in this event or you're in this event. There was no overlap because nothing in there can occur at the same time. Okay, so in red, let's talk about what it means to be independent events. And I like to think about influence in this case. Like the two events don't influence each other, and further, they don't provide any knowledge about one another. So events have no effect on each other. But they can definitely occur at the same time. An easy example of this that we already talked about, eye color and height. These two events definitely have no effect on each other, but there's definitely brown-eyed people that are above 6 feet tall, so there's definitely overlap within these two events. So just because you're independent doesn't mean there's no overlap. It just means these two variables, these two events, have no effect on each other. All right, let's take a look at example 2, the first trimester screen. It says the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a false positive result. Among 100 women with normal pregnancies, what is the probability that there will be at least one false positive test? So the probability of at least one false positive. Okay, so I want to cue you in on a code word here, or a key word here for probability. The word at least or at most. When you see those, a lot of times you can use the complement rule and it's a lot easier. So the probability that at least one false positive, so that means there could be 1, 2, 3, 99, or even 100 false positives. That's a lot of probabilities to calculate. But if you go the other way and use the complement rule, the probability of at least one false positive, so the opposite of that statement would be the probability that there's no false positives. So if we can just do the complement, so 1 minus the probability that there's no false positives, that's probably the most efficient way to get to this answer. Okay, well, the test results are definitely independent. So I want to make that note before we actually start multiplying out probabilities here. It's definitely reasonable to assume that women, 100 women that are sampled here, their pregnancies are definitely independent of one another. Okay, so for there to be no false positives, that means all 100 women, there we go, they all have a 95% chance of being correct. So I'm just going to do 1 minus, and then I got 0.95, 0.95, dot, 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 0.95, skip a few there, right? And that represents my 100 women. Or the simple calculation with that is just replace this with 0.95 to the power of 100. So 1 minus 0.95 to the power of 100. So the complement rule, simple, effective way to calculate this probability, which is approximately 0.9941. That's the probability that there'll be at least one false positive. So to give that answer some context, there's over a 99% chance that at least one woman will have a false positive. So when you see key phrases like at least or at most, a lot of times it's more efficient to use the complement rule and do 1 minus the probability that there's none. All right, example 3, weather conditions. On a recent day, the Daily Herald forecasts a 50% chance of rain in Roselle and a 50% chance of rain in Bloomingdale. What is the probability it will rain in both locations? Okay, I don't want to say this is a trick question, but this one requires probably a little bit more thought than just the plug and chug, because the answer is definitely not just 0.25. So you can't simply say, just multiply these two probabilities, 0.5 times 0.5, and get 0.25. And the reason is this multiplication rule applies for independent events. But the weather in Roselle and the weather in Bloomingdale, those are definitely related. Those are neighboring communities. So if it rained in Roselle, there's a really good chance it rained in Bloomingdale, and likewise for Bloomingdale to Roselle. So these events aren't independent, so we can't just multiply 0.5 times 0.5 equals 0.25, because they are not independent. In fact, it would be a much higher probability, probably. So the actual probability would be higher than 0.25. And again, don't be fooled by the setup of these types of problems. Roselle and Bloomingdale weather, definitely not completely independent of each other. Very much related. Okay, example 4 about allergies. It says, is there a relationship between gender and having allergies? To find out, we use the random sampler at the United States Census at school website to randomly select 40 U.S. high school students who completed a survey. The two-way table shows the gender of each student and whether the student has allergies. So there's our two-way table. And it says randomly select a student from the sample and consider the events A, the student has allergies, and F, the student is female. So to help us with all three of these probability questions, let's go ahead and complete this two-way table and add the total row and the total column. So the total number of females, 23, total number of males, 17, and then the total rows here. So total number of kids with allergies, that's 18, and then no allergies, that's 22. And then our table total down here, the overall total, that should add up to 40. Okay, so A represents the student had allergies, F represents the student is female. So part A says find the probability of A, which would be probability a student has allergies. So it looks like 10, 8, totals 18 out of the 40 kids had allergies. So that's just a basic probability. Probability you select a kid out of here that has allergies would be 18 out of 40. Probability the student's a female, so go to the female column. Total number of females in the sample was 23, so 23 out of 40. Okay, so those are pretty basic, those are pretty straightforward. But how about these? So part B says the probability that they have allergies given that they are a female. Probability of allergies given that you are female. So now we need to focus strictly on the column that is females. So this column here. So given our condition, female, that's where we're looking, what's the probability that you had allergies? So there's 23 total females, 10 of them had allergies, so that would be 10 out of 23. Now we're going to flip those events. What's the probability of F given A? So what's the probability you're a female given that you have allergies? So now our condition that we're looking for is allergies. So let's go to the total people with allergies. That's the allergies row here. So I'm going to highlight the allergies row. That's a total of 18. And then looks like females in that group was 10. So of the people with allergies, there were 10 females. So 10 out of 18. Okay, so part A, we found the basic probabilities just out of the total in the table. Kid with allergies, or a kid that's a female. Part B, we found a couple conditional probabilities. Notice how the totals are different, because we looked at specific conditions. And now the interesting part, part C. Are the events A, kid has allergies, and F, the student is female, independent? Explain. So in our justification as to whether or not these two events are independent, we're not looking for like a wordy, your medical professional opinion about whether those are like female and allergies independent. So don't just say something like, gender and allergies are definitely independent because that depends on genetics and has nothing to do with your gender and so on and so forth. Don't go down that road, okay? You're a statistician, so you need to prove this mathematically. And we actually, since we've already talked about this, here's what we got to show. If they're independent, then the conditional probability, like probability that A happens, given that F has already occurred, would just be the probability of A. So it's almost like F had no effect. Likewise, for the probability that F happens, given that A has already occurred, that would have to just be the probability of F. So it's almost like A never even affected it. But in our case, this probability definitely doesn't equal this probability, and this probability definitely doesn't equal this probability. So these are not equal. So what does that show? Well, that proves that A and F are not independent because their conditional probabilities are not equal to their individual probabilities. If they were, like if these simplified to be equal, then yeah, they totally would be. And if you can't tell that just by looking at the fractions, let's go ahead and provide the decimals for these. Like the probability of A given F, 10 divided by 23, and the probability of A is 18 over 40. So if we just provide the decimal values for those, like we can see right away, they're not equal. And the same goes for these. We can justify it by just providing the decimal values. So this is the only way to prove that events are independent or whether they're not independent. Since these are not equal, these probabilities, they're definitely not independent. Okay, that's all for these notes. I'll see you in class.